That said, there is a tiny sliver of a silver lining in my forgetfulness, and that is that it gives me a good lead-in into this talk, which is about mathematics and computation. But what it's really about is how not to forget things. If you've been to previous talks in this series, you will have seen a picture similar to this one. Really, it's sort of the big picture of the timeline of the history of science, which divides into more or less 3 parts. I was really hoping that I could have that on the screen there and my notes on the screen here, but that's not going to work out. So here I'm just going to have to wing it. So you've got the Greeks from about 500 BC to 170 AD, followed by the Dark Ages, the so-called Dark Ages, where not much happened, followed by the modern era starting at about 1543 or so with Copernicus. The story of mathematics predates all of that by a very wide margin. Math goes back tens of thousands of years. And also in contrast to the story of science, where science arose only in a few places on Earth, math is ubiquitous. All human societies invent math. And not only that, they all invent the same math. So there is no Western math and Eastern math. There's just math. It's universal. And if you think about it, it's actually not so hard to see why that would be. Because if you are a prehistoric nomadic goat herder, for example, your survival is not going to depend on knowing the exact distance from the Earth to the Moon, but it might depend on knowing that the number of goats that you had when you woke up was the same as the number of goats that you had when you went to sleep the night before. And so if you're forgetful, like me, you might invent some technology to help you out. And so one of the things that you might do as a prehistoric goat herder who has not had the benefit of a high school mathematics education is take a clay pot. And as you bring your goats or your sheep into their enclosure for the night, as every sheep comes in, you put a pebble into the pot. And in the morning, you reverse the procedure. As the sheep comes out, for every sheep that comes out, you take a pebble out of the pot. And if the last sheep comes out at the same time as the last pebble, then you're good. And this is actually what people did. And that's actually where we get the word calculate. Calculate derives from the Latin term calculus, which means pebble. And that's where calculate and calcium and the calculus on your teeth, all have the same Latin root. Anyway, so this talk is about how those pebbles turned into modern mathematics and computers. So it's part of, as the intro said, it's part of a series of talks that we're kind of in the middle here. This is about mathematics and computers, and it starts tens of thousands of years ago. We don't really know when. The earliest artifact that we have that demonstrates that humans were doing arithmetic is this artifact here. It's called the Ishango bone. It's been dated back to about 20,000 BCE. But these sorts of things occur. There's just gobs on here. This is a clay tablet that dates back to 1800 BCE, so about 1,000 years before the dawn, more than 1,000 years before the dawn of science. It's called Plimpton 322, after the guy who owns it. So Babylonian numbers, they look like this, and the reason they look like this is because of the medium that Babylonians used to write their numbers down in. They used clay tablets, so they made numbers that were easy to write down in clay. Here is a papyrus from Egypt, 1600 BCE, so 1,000 years before the start of science. Egyptian numbers, they look like this. In fact, here you can actually read off this number that's carved into this stone wall here. It's 1,333,331. Not sure exactly what that number indicates, but Greeks had their own system of numerals. Alongside with arithmetic, the other important early mathematical development was geometry. This is Euclid's Elements, dating from about 500 BC. And it's also easy to see why geometry would develop along with arithmetic, because if you're a farmer, it can be important to know how to divide up your fields so that you get the right amount of crops. Geometry means literally measurement of the earth, geometry. because that's what it was developed for, so that farmers could divide up their land equally. This is a papyrus fragment of an actual manuscript of Euclid that dates back to about 200, 300 AD, about 700 years after Euclid actually wrote it. So this is a copy of a copy of a copy. We don't have the originals. They're long lost. Roman numerals you're all familiar with. There are Chinese numerals. They look like this. These are Mayan numerals. And Mayan numerals have an interesting feature. Here's a clearer transcription of them. Anybody notice something different about Mayan numerals that has not, zero. The Mayans were the first known civilization to invent an actual symbol for the number zero. There's a lot of precedent. Before that, what people did when they had to write down a zero is they just left the space where the number would be blank. And the Mayans were the first to actually write something to indicate zero. And that is one of the really key technological developments, because of course today, our world is ones and zeros and we're familiar with that. But at the time, zero was kind of a crazy, controversial notion, because how can you write something that indicates the absence of everything? And philosophers actually debated this for a very long time. So blank columns to denote zero go back to about 2000 BCE. But the first record of a zero symbol is 300 BCE in Babylon. The modern zero starts in India around 700 AD. It migrated to China and then to the Middle East, where it was first made respectable by this gentleman, Muhammad ibn Musa al-Khwarizmi, as best as I can reconstruct it. He was an Arabic mathematician who, among other achievements, invented and first wrote down the rules of algebra. And in fact, we get our name for algebra from the Arabic word al-jabar, which means the joining of broken parts. And from al-Khwarizmi, try this again, al-Khwarizmi's name, we get the modern word algorithm. He formalized the mathematics of zeros. He introduced the Arabic numerals, which are now ubiquitous in the world today. So all the numbers that are now in use throughout human civilization were essentially invented by this guy. Together with the invention of mathematics itself came the invention of machines to help people perform mathematical calculations. The Ishango bone I've already mentioned. More sophisticated tools like the abacus date back to about 500 BCE. And again, this is an invention that was independently invented in many times in many places. This is a Roman abacus. And it's interesting because it's actually using a place system. So here's the units place, the tens place, the hundreds place. And there's this little piece over here is what they used for calculating with fractions. So they're starting to invent fractions, which again at the time with Roman numerals, those are really difficult to work with. So this is sort of one of the world's first digital computers. And the reason it's called digital is because you used your digits in order to run it. This is an early computer dating to about 70 BC called the Antikythera mechanism, after the place that it was found. It is an analog computer made of gears. Here's a modern reconstruction. It was used for astronomical calculations. This is not a digital computer, it's an analog computer. But it is a computer. It is a machine that does computations, in this case astronomical calculations. People built lots of different kinds of these. This is a similar kind of machine called an orrery. This one is a particularly sophisticated one. But these were constructed by people starting in about the same time. 70 BC was the Antikythera mechanism, the earliest known example of this kind of thing. But you can actually still buy these today. They're used as decorative objects rather than actual useful tools. But they were actually used as computers for hundreds of years, thousands of years. And that was pretty much the state of the art up until the mid-1500s, when we leave the Dark Ages and enter the era of modern scientific development with the advent of Copernicus. And the first interesting development in mathematics at that time was the invention of logarithms by John Napier. Is anyone here who does not know what a logarithm is? Okay, in the interest of time, then I'm going to skip the explanation of what a logarithm is and just go on to tell you that a fellow named William Oughtred used Napier's idea of a logarithm to invent the slide rule, which again became the state of the art in calculating machines up through about the mid-1950s and into the 60s. At NASA, to launch the Apollo, during the Apollo era, engineers were still using slide rules in day-to-day work. So this invention had this technology had a useful life of about 500 years. This is just a slide of a paper slide rule that I put in here in order to explain, if I were going to get into the details of how logarithms work. Basically, logarithms let you take multiplication and turn it into addition. And when you turn it into addition, you can just slide two scales around if they're denoted in logarithmic scales and do multiplication that way, much faster than you can do it manually. The next development came about 100 years later with Blaise Pascal, who you could do an entire series of talks just about him. He was one of the great mathematicians of all time. He invented more stuff than I could possibly even list in the time available to me. But one of the things he invented was another digital computer. This is the plan for it, and here is, I can't remember whether this is an original or a modern reconstruction, but this is what it looks like. And instead of being used like an abacus, it's also based on gears, but it's digital because the exact position of the gear doesn't matter. The position of the gears are digitized into particular positions that display exact numbers in the results, the output display here. This idea was expanded by Charles Babbage, who invented a device that he called two devices. The first one's called the difference engine. This is a little piece of the difference engine and a modern reconstruction of it. It was actually never built in Babbage's time. He just drew up the plans. This is a full-sized actual working model of a difference engine. It's a modern reconstruction of it, but it actually works. There used to be one at the Computer History Museum, but unfortunately it was on loan and the owner took it away, which is very sad. But I think there's still one up in the Computer Museum up in Seattle. And if you ever get a chance to see one, it's really interesting to watch it work, because you put in the thing you wanted to calculate, and then you turn this huge crank, and the whole thing just looks like this steampunk fantasy, but it's real, and it's worth seeing if you ever get a chance. The same principle behind the difference engine was also used in modern times to build this little handheld version. This is like the iPhone of the 1940s, the Curta mechanical calculator. It's essentially the same idea, but shrunk down really small, and instead of the giant crank that you have to use two hands to turn, there's this little tiny crank up top that you can turn with your fingers. But it does essentially the same thing. I'm going to take a little detour here from computers back into math and ask a philosophical question. This series of talks is about the history of science, and so philosophers have been asking for a long time, is mathematics actually a science? The science is the study of the natural world, but mathematics is the study of abstract entities like numbers and geometrical shapes, which of course has application to the natural world, but it is not actually the process of mathematics itself. Is debatable or whether it's a science. But that process is a natural phenomenon. And so the study of the process of doing mathematics, that is a science, and that is called meta-mathematics. So if you're studying math scientifically, you're doing meta-mathematics, and that's a science. And I want to give you just a little bit of a flavor of what a meta-mathematical analysis looks like. And trust me, this will actually turn out to be important later in the talk. So as rational people, we have this instinctive aversion to contradictions. We don't like it when our reasoning leads us to conclude that something is true and its negation is also true. But it turns out there's actually a good reason for our aversion, and that is this, that contradictions are actually fatal, because if you get to any contradiction, then you can reason logically to any conclusion, and here's how you show that. Let's suppose that we get to a place where we have concluded that some proposition P and its negation not P are both true. If they're both true, then the proposition P itself is true by itself, because if two statements are true, then each one is true individually. Therefore, the proposition P or Q must be true, because a disjunction is true if any one of its components is true, and we know that one of the components of P or Q is true, namely P. And therefore, Q must be true because not P is true. Right? So P or Q, one of these must be true, is not P, so it must be Q. And Q can be anything. So if we get to a contradiction, then then everything is true, and we cannot rule out anything logically, and so that's why contradictions are fatal. I'm going to show you an example of how to apply this. So this is a discovery made by the ancient Greeks, that the square root of 2 is an irrational number, which is to say that there are no two integers, a and b, whose ratio squared is 2. So the way you prove that is you assume that it is true. You assume that we have two integers, a and b, that we can square and get 2. And we also assume that this fraction is in the lowest common form. So we have a and b have no common factors. So we do a little algebra and conclude that a squared equals 2b squared. And so a squared must be an even number. And so a must be an even number because odd numbers squared are odd numbers. So if the square of a is even, a itself must be even. So it must be 2 times some other number, and let's call that other number c. So a squared is 2c squared, which is 4c squared, which is 2b squared from up here. And so 2c squared is b squared. And so b squared is 2 times some number, so b squared must be even. And so b must be even. And so a and b are both even, and so they must have a common factor, namely 2. But we assumed up here that they have no common factor, so now we've gotten to a contradiction. And so the assumption that we made in order to reach that contradiction cannot be true, and that's how we know that the square root of 2 is irrational. This caused scandal among the ancient Greeks. They tried to suppress this knowledge. They thought it was horrible, ungodly. It was a big deal back then. But this kind of reasoning was carried out throughout, mainly through the 17th and 18th century, in an attempt to get to a pure mathematics that we could prove had no contradictions. And so we could rely on its results. And this effort reached, I could give an entire talk about just that, but the effort reached a climax with this fellow, Friedrich Ludwig Gottlob Frege. And he wrote this book called Grundlagen der Arithmetik, wrote it in German. And he thought he had it all figured out. So he developed mathematics starting with set theory as its foundation, because if you figured that let's just try to assume the simplest thing we possibly can, and the simplest thing that he could think of was a set. A set is a collection of things, and that's all he assumed, and built up all of mathematics from set theory, thought he had it all figured out, started sending out manuscripts for review, and one of those manuscripts ended up in the hands of this gentleman, Bertrand Russell. And he said, this all looks pretty good, but I see there's a little snag. And the snag is something called Russell's paradox. And the Russell's paradox goes like this. Some sets contain themselves as members. So in particular, for example, the set of all sets must have itself as a member, because the set of all sets is a set. And so it must be a member of the set of all sets. So then he asked, does the set of all sets that do not include themselves as members include itself as a member? And if you think this through, the set of all sets that don't include themselves as members, like the set of all numbers, for example, the set of all numbers has only numbers in it, so it has no sets in it, so it can't have itself as a member. Seems like an unproblematic notion, but the set of all sets that don't include themselves as members must include itself as a member if and only if it does not include itself as a member. Right? You get into this weird loop. You can't decide. If it doesn't include itself as a member, then it must be a member of the set of all sets that don't include themselves as members. A simpler version of this is a barber shaves all people who don't shave themselves. Does the barber shave himself? Or if the barber shaves himself, then he doesn't shave himself, and if he doesn't shave himself, then he does shave himself. This kind of strange loop caused a crisis in mathematics, and Bertrand Russell and Russell Whitehead. I forget Whitehead's first name. Alfred. I forget. See? Wrote this 3-volume set, Principia Mathematica, where they tried to sort all this out in a different way. It is no one reads this today. Just to give you a flavor of what's inside it, this is one famous excerpt from inside this 3-volume set. And at the end here, this is like the middle of volume 2, they say, from this proposition it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. So this, 1.5 volumes to get to that point. And it turned out that this effort had a fatal flaw in it too, which is why no one reads this today. It's just of historical interest. And that was discovered not by this fellow directly. This guy, David Hilbert, is the guy who organized the effort to try to fix this once and for all. He designed something he called Hilbert's program. So just to give you a rough timeline here, in 1903, Russell discovered Russell's paradox. Principia Mathematica was written between 1910 and 1913, and in 1920 to 1921, David Hilbert proposed this program to try to prove that math is consistent, complete, and decidable, which is to say that it contains no contradictions, that all true statements can be proved formally, and that this can be done algorithmically. So we wanted to find a procedure to find a formal proof for any proposition that you wanted to decide whether it was true or false. 10 years after he first proposed this problem, this fellow, Kurt Gödel, proved that it couldn't be done with his famous incompleteness theorems, published in 1931. This is just the formal statement. Any consistent formal system F within which a certain amount of elementary arithmetic can be carried out is incomplete, i.e. there are statements in the language of F which can neither be proved nor disproved in F. If you go back and read Gödel's original formulation, it's even more complicated than that, and it's in German. But what it means informally is no formal system can prove its own consistency. So this thing that we would like to be able to do, we can't do it. And we can prove that we can't do it. Which is kind of interesting. And this also has caused called for a lot of philosophical debate about whether this proves that humans can do things that computers can't. I'm not going to get into that. What I am going to mention, though, is getting back to the history of computers. 5 years after Gödel, the next important development was made by this gentleman, Alan Turing. Alan Turing was a cryptographer. He was best known at the time for inventing this machine, which he called the bomb, written with an E at the end, which was a special purpose machine, much like the difference engine or the analytical engine or Pascal's computer or Orary's. It was special purpose, designed for breaking German codes, and in particular breaking the German Enigma code. It was a unitasker. This is what the inside of it looks like. And with this, Alan Turing and his team successfully broke the German codes and arguably helped win World War II and defeat the Nazis. But before he did that, he wrote this paper, which nobody outside of the field has ever heard about. It's called On Computable Numbers with an Application to the Entscheidungsproblem, which is the German word for the decidability problem, which is the problem that Kurt Gödel worked on and proved could not be solved. In this paper, Turing describes a new kind of calculating machine, which now, he didn't call it this, but nowadays we call it a Turing machine. This is an actual working Turing machine. It consists of an infinitely long, nominally an infinitely long tape. Obviously, you can't physically build an infinitely long tape, but it consists of this tape onto which the machine can write ones and zeros. And there's a camera up here that can look at the tape and see what symbol is at the point on the tape that's inside the machine's mechanism. And then there's a control system, which is off screen right now, which does a very straightforward thing, which is it looks at the symbol on the tape, and then based on a table, it either rewrites that symbol, erases that symbol, and writes the other symbol on there, and then it moves the tape left or right, and then it goes to a different state in that table. And that's it. That's all it does. Here is another example of a Turing machine. This one's made out of wood. And this one is interesting because you can actually see the control mechanism. It's up here. So this is the table. And you program this thing by putting these pins into this table. And this is literally a mechanical computing machine, very much in the spirit of the other mechanical computing machines that we've seen up to this point. Except this one is different. And it's different for two important reasons. The first one is that Turing showed that a Turing machine can compute any computable function. And I'm not going to go into the proof of how you prove that. Basically, the way you prove it is the hard way. Is you make a list of all of the possible ways that you could, even in principle, compute something, and then you show how this machine can do it by actually writing the code, he actually generated the tables for every single step in the process for producing any conceivable computable function. Despite the fact that you can prove that this machine can compute any computable function, you can also show that there are things that this machine can't compute. It's a result analogous to Gödel's result for mathematics. So Gödel showed that there are things that you can't formally prove. Turing showed that there are functions that you can define, but that you cannot actually compute. And the most famous example of this is something called the halting problem. So a Turing machine cannot tell, if you give a Turing machine as input a description of another Turing machine and ask it, is this Turing machine going to stop and produce a result, or will it run forever? That question cannot be answered by a Turing machine. And the third, and arguably most important result, is that there exists a universal Turing machine, which is to say that there is a table that you can build that lets this Turing machine with this table do the computation of any other Turing machine with any other table. And the way you do that is you describe the table of the other Turing machine on the tape. So instead of having to build a control mechanism for every problem we want to solve, we can now program this machine just by putting ones and zeros on the tape. And the reason this is important is because if we build this machine, it's the last machine we'll ever have to build. Right? I mean, all these machines, when I talk about building these machines, I'm talking about you have to actually build them. You have to grind the gears and make them all. This machine, you build one and you're done. Now you can just write software. So Turing basically invented the notion of software. Actually, Kurt Gödel really invented the notion, but he didn't realize that that's what he had done. Turing made it explicit. And the other reason this is important is because once you realize this, then you realize you don't have to build a Turing machine that literally looks like the thing that you described. Any mechanism that does the same thing will do. And of course, building the actual mechanism with a physical tape that's not the best way to build one of these machines. The best way to build one of these machines is with vacuum tubes and transistors. And so that's, of course, what we did. This is the first real Turing machine. It's the ENIAC. It was built in 1945. It had 20,000 vacuum tubes. And that started the avalanche of technological progress that we're all familiar with today. I'm going to just blast through a few of the highlights here because despite the fact that this is recent history and all this happened within living memory, and even within living memory of many of the people who are in this room, I think it's worth being explicit about it because it gives you a little bit of perspective about the importance of the times we live in. There will come a time in the future when everything that I'm about to describe to you here will be ancient history, as ancient as the history that I've gone through up to this point. But we're actually living through this transition where we don't have to build mechanical computers anymore. And it's all because Alan Turing figured out how to do it. So we went from vacuum tubes to discrete transistors from 1954 to about 1970. This is when computers filled rooms and had spinning magnetic tapes, which actually very much in the spirit of the original Turing machine. To microprocessors. The first microprocessor was introduced in 1971 by Intel. This is an actual picture of it. And it's interesting because in this picture you can still make out individual transistors. There are, let's see. Oh, yeah, next slide. So this is what it looked like when you actually bought it in 1971. The 4004 had 2,300 transistors. And just to compare it to a modern CPU, not even state-of-the-art, 5 years ago, had 10 billion transistors. Yeah, I know, it's mind-boggling, isn't it? First pocket calculator, the first scientific calculator was introduced by Hewlett-Packard in 1972. The first personal computer with an 8-bit CPU, the MSI 8080, was introduced in 1974, and that led to the PC revolution. You know, the Apple I came out in 1976, the Apple II, 1977, not that long ago. People forget there were lots of other competitors at the time. It was not a foregone conclusion that Apple was going to be the one to come out as the big winner from all this. And in fact, it almost didn't, because in 1981, IBM introduced the IBM PC, and for a long time it looked like that was going to be the big winner. The iPhone was introduced in 2007, only 12 years ago. It's kind of mind-boggling, isn't it? And that's the world we live in today. And it was all made possible by this guy and his paper. And I want to close with a couple of other little bits of trivia about Alan Turing's life. Because despite the fact that we owe him, human civilization owes this man a much bigger debt than most people appreciate. Not only did he help the Allies win World War II, but he basically invented modern computing and the computer revolution that drives the modern economy. But Alan Turing was a homosexual. And he was a homosexual at a time when that was not looked kindly upon. In 1952, he was convicted of gross indecency, which was a crime. And he was sentenced to forced chemical castration. And 2 years later, he committed suicide at age 41. It took 55 years for the British government to issue an apology, which was done by the Prime Minister Gordon Brown in 2009, and another 4 years for the Queen to issue a formal pardon for Turing's conviction.
Oh, good what? Dead.
And I think that's worth being more widely known and reflected upon.
Yeah, hi. Great talk. Could you please put in a plug for the Computer History Museum? Because it'll walk you through all the history that you went through, and you can actually see the exhibits.
Yeah, go to the Computer History Museum. It's right here in Mountain View. It's a tremendous resource. It was even more tremendous when they had the difference engine there that you could watch. But it's still awesome. Go there. And there's also one in Seattle which is also worth. I've never been there. It's on my bucket list.
I guess I made a mistake if you heard me say I have a 4004. What I have at home is the machine language coding for functions of add and plus for a 4004.
So a couple of comments. One is that mathematics is usually known as the queen of the sciences rather than a science. That it's paired with the sciences but isn't one. And the other comment is that the computability of things is over a ring. So that computability that you were showing is the computability for digital computers, but if you compute over reals or something like that, you get a different kind of computability.
Okay, that's getting into some pretty esoteric issues, which I'm guessing most people are not going to be interested in. So why don't we take that offline?
I've always been impressed by all these geniuses over the last 1,000 of years,
Me too.
including up to date. But my experience has been quite different. I got my bachelor's in mining engineering at Stanford in '47, and subsequently a master's in metallurgy. But my experience has been quite different. The mining department required as much math as all the physicists did. But the experience I've had subsequently putting in time with Lockheed and GE, the only mathematics I ever actually used was adding and subtracting and multiplying and dividing, period.
This is the interesting thing.
Ridiculous.
Is that you can actually build everything out of that. You can build every mathematical concept that has ever been invented by humans. Ultimately boils down to adding and subtracting, which then ultimately boil down to counting. And one of the interesting things about Turing machines is that there's so many different ways that you can build them. And one of the ways that you can build them is to have a machine with two counters. That's all you need. And the ability to test. You can count up and down. You have to be able to count up and down and test if one of the counters or the other is 0. And with that, you can compute anything. That's all you need. Yeah. Sorry, hand here.
I can't see the hand. Who's
Right here,
there?
front row.
Is there a chance that you would agree with the following statement? Nobody is a genius. Like when you did the proof of there's no irrational number, it requires remembering what you just did and going step by step through something. If you are given good information and you are willing to put forth the hard effort, you can do this too. People like to think they can't do math. They don't try. It's too hard.
Yes. Math, all this stuff is much easier than it's generally made out to be. Even rocket science isn't really rocket science. But I don't agree that there's no such thing as genius. The genius it comes from being the first person to figure something out. Because in retrospect, all this stuff that Alan Turing did is kind of obvious, especially when you have easy access to Turing machines, when they're ubiquitous, when they're surrounding your life, then it becomes kind of obvious. But if you're living in a world that doesn't already have all this infrastructure, I think it takes a certain spark of genius to imagine it for the first time. And that's why it took 20,000 years for it to happen.
Any other? Here we are.
I was so struck by the treatment that you described of Alan Turing that I feel that our society is lacking and still is lacking to a great degree, even though we appreciate the genius and the invention of people who worked on these discoveries. We can't develop enough socially to accept human beings as they are, and I hope that this will occur before the end of the century.
Yeah.
Thank you for all that you said.
And again, it really boggles my mind. They did this to Turing, and he was a war hero. You know?
I like the demonstration of the most primitive math that you brought forth, but there's a math I've heard of. I don't know why you didn't mention it. I think it precedes the Babylonians, and they counted on the 3 digits of their fingers, which comes out to 12, and so it was like a base 12, and that's why our clocks go to 12.
Yeah, sure.
Could you say to inform us about that?
That's not really different. It's a variation on the theme. So before you even get to the idea of a base, you have to invent the notion of a notation where the position that a symbol sits in matters. And it took a while for people to even figure that out. So if you think about, for example, Roman numerals, if you take the symbols in a Roman numeral and you rearrange them with a couple of restrictions, you end up with the same numeral. Now, there's a convention of putting the big numbers on the left and the little numbers on the right. But if you have a number, for example, that starts with M, and you put the M on the right, you can tell that you've moved the symbol because it's in the wrong place, and you can also still reconstruct the original number. You can't do that with Arabic numerals. With Arabic numerals, if you rearrange the numbers, you always end up with another number that's a different number. And that property turns out to be crucially important for inventing algorithms for adding and multiplying and whatever. And part of making that work is picking a number as the base of your system, saying that the number here is units, and the number here is 10s or 12s or 60s or 16s or 8s or whatever. And the number here is that base squared, and the number here is that base cubed. The actual number that you choose for your base doesn't matter. That's not the important development. The important development is coming up with the idea of having this base arithmetic at all. And that was also independently discovered by various civilizations at various times, but it was Al-Khwarizmi who first really popularized it. His work that spread throughout the world and became the modern numbering system that we use today. And he used base 10, and that's why we use base 10.
This was all described wonderfully by Tom Lehrer in a song he wrote called The New Math. If you have a chance, Google it. It's the funniest thing. But I wanted to mention, you showed a picture of the HP computer, the pocket computer, which was all the rage in the 1970s because it had this innovative reverse Polish notation, which it was very attractive to scientists in particular. A colleague of mine at Stanford wanted to buy an HP pocket calculator, put in a requisition. The word came back, you can't buy a brand. We decide what brand. You decide the performance you want. So she put in, I need a computer with reverse Polish notation. That would specify HP because nobody else used it. The answer came back, we don't buy foreign computers.
I remember I bought one of those early ones, and I believe they were $395, which would make them around, at least $2,000 today.
My name is Dick Hewitson. I just want to thank you. Somebody else has already mentioned it, but I have been a gay activist for years and years and years, and had many, many friends who have died by suicide, 2 of them within the last decade. So I really appreciate your pointing out this part of Alan Turing's life. Thank you.
Yeah, I'd like to remind everybody that the human brain and brain of all mammals, or of all animals, do pattern classification. In nature, that is the most proficient and fastest way of getting things done. Now, the reason why mathematics is so hard is that you have to use pattern, you cheat, you use pattern classification in order to do calculation, and that is really hard.
Yeah, I mean, it's really boggles my mind. They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war hero. You know? They did this to Turing, and he was a war h That's why we build machines to do it for us.
I'm not a gay activist. I'm a straight person all my life. But I'm a
It's
history.
not a showstopper.
I'm a history person, though. And they made movies about Alan Turing. They've also made movies about Lawrence of Arabia, who was one of the most famous soldiers of World War I, and he was most likely gay.
Actually, Jeff said that, The Imitation Game is the name of the movie for Alan Turing. Good movie. The other thing I just really want to say, that's a great talk you did. 45 minutes of thousands of years. It's unbelievable.
Yeah, it's a challenge.
And it was quite recognizable as far as, my intelligence.
Thank you.
Thank you.
Yeah, thank you, too. Those were facts, not philosophy. I read a book by Alan Turing's mother showing that he did not commit suicide.
Okay, that's probably something else we should deal with offline.
I know, but she was...
Yeah, Jerry Grass. Why does it matter whether math is a science or not?
People care. Some people seem to care about it. I'm not one of them, but I thought I would mention it just because there's a long history of philosophy professors arguing about it. So I thought I'd give that debate some lip service. That's all.
In that context, maybe it's because there's no Nobel Prize for mathematics. There is the Fields Medal, which was won just a few years ago, for the first time in its 40 years of being issued, won by a woman, an Iranian woman, it turned out. So, very interesting.
Mm-hmm. Anybody else have any questions? We have so much time, the luxury, you can maybe make a comment.
Yes, your bio says you made a movie on homelessness. Now, why does a technical person like you suddenly get such a draw to make such a commitment of yourself in such an area? And how did you get the artistic talents from a technical background to perform that?
Well, the answer to why was morbid fascination. I was living in LA and was just curious how people ended up on the street, and the only way that I could work up the courage to go up and ask one of them was to use a camera as a shield. And how I got the knowledge how to do it was trial by fire. I just grabbed a camera and started doing it and learned on the job. That movie was my substitute for film school. But you live in LA long enough and you have to make a movie or they throw you out.
Anybody else have any questions or comments? We have about 15 minutes, so. Okay.
You told me to keep it short. I guess I overdid it. Oh, you know what? I could actually talk about the proof that the halting problem is unsolvable. If we completely run out of other things to talk about, I have a backup slide for that.
Show of hands.
I think it's kind of interesting. It's not that hard to understand, especially nowadays.
Go ahead.
Yeah. Okay. So here's how you do. This proof was really hard in Turing's day because he had to invent the entire notion of a computer program and formally describe what it was to people who had no idea, had never encountered this concept before in their lives. But nowadays, computer programs are ubiquitous and familiar, and so proving this theorem is pretty straightforward. And we do it in exactly the same way that we proved that the square root of 2 is irrational, by assuming that it's not true and showing that that leads to a contradiction. So we assume that we can solve the halting problem, which is to say that there exists some program, which we're going to call H for halting, that solves the halting problem. That is, H takes as input 2 parameters, which is a program P and an input I, and returns true if P halts when run on input I, false otherwise. Everybody with me so far? All right, so now we're going to construct a new program that we're going to call B for no particular reason. that does the following. So B takes as input a program P and calls H as a subroutine with P as a copy of P as both of the inputs. So it computes H of P, which is to say, calls H as a subroutine to determine if program P, halts when run on a copy of itself as the input. And that was a really mind-bending notion in Turing's day and took pages and pages of paper to describe. But nowadays, if you're familiar with compilers, a compiler is a program, and most compilers can now compile themselves. So think of a compiler compiling itself as an example of a program running on a copy of itself as its input. So B is going to call this subroutine, and then it's going to get the result, either true or false. And then B is going to look at that result and return the opposite. So if H says that P run on a copy of itself is going to halt, then B is going to run forever. It's going to enter an infinite loop. Otherwise, it's going to return and stop and return some value. Now consider what happens if we run B on a copy of itself. And what's going to happen here is exactly the same thing as we saw in Russell's paradox and the barber who doesn't shave himself. We're going to get into this weird infinite loop. B will halt if and only if H of BB, so because we're running B of the copy of itself as an input, and B takes that input and sends it to H. So H is now running with a copy of B as its input. It will halt only if H of BB is false. But H of BB is false only if B doesn't halt. So it halts only if it doesn't halt. So it's a contradiction. Therefore, our assumption is false, and we cannot build H. That's it. Easy. It's easy once you know how.
I had a question. I was a math major, and there's something different about math in the enthusiasm that professors have for it and the elegance of a proof. I've never heard of elegance with another field like that. Can you talk about the enthusiasm of mathematicians and the joy of elegant proofs?
I'm so glad you asked that, because this result is not the end of the story. This is the beginning of a whole other story of discovery, one branch of which is the study of efficiency. So once you've got this notion of a computer program, you start to care about things like, how do you write a program that solves a particular problem in the shortest amount of time, or with the fewest amounts of lines of code. And you start to ask, can we figure out if we've got the program that solves some particular problem most efficiently by some metric? And the answer to that turns out to be no, we can't. And that's a consequence of this, plus another new concept introduced by a fellow named Gregory Chaitin that he called elegance. So you can actually produce a proof, and unfortunately I didn't bring it with me, but it's about the same length, and I've got a web page that has it, but you could probably even figure it out on your own at this point, where you introduce the concept of an elegance checker rather than a halting checker. So you assume that you have some program that you feed another program into, and it tells you if this program is the shortest one that produces the output that program produces. And then you go through some steps to show how you would, if you had that information, how you could use that to produce a shorter program that produces the same output. And therefore, the elegance checker must have lied to you when it told you that that the program that you gave it was the shortest one. Because if you had that elegance checker, you could use the elegance checker to produce a shorter program if it was reliable. But you can't, so it can't be reliable.
The other thing, when I was an undergraduate, is the professor would say, this leads to this, leads to that, and he'd be doing it in a pure space. He says, now the real world is different than this, and he said, who cares about the real world? It's an elegant proof.
On a similar subject, you've given talks about physics too, and there's a popular book that came out last year called Lost in Math, where a physicist reports, this is a comment more than a question, but we have time. Sabine Hassenfelder comments that physicists search for new theories by looking through elegant theories. They like to believe that the world is elegant or beautiful, and so they disregard everything that's not elegant or beautiful.
It's actually more than that. This is an interesting observation.
Right.
It just turns out that the best theories that we have on the evidence just turn out to be very elegant and concise. And this is a very interesting fact about the universe. It didn't have to be that way, but it just turns out that way. And it's a bit of a head scratcher why whether the fact that it turns out that way is an indication of some kind of deeper truth. And I'm trying to remember the name of the guy. There's a famous paper called The Unreasonable Effectiveness of Mathematics in the Physical Sciences by, I think it was James Wheeler, but I'm not 100% sure about that, where he talks about exactly that question. It's worth looking that paper up and reading it. It's still kind of an open problem. One possibility is that that the universe really actually is, in some kind of deep sense, a computer that's running a simple program. And there are some branches of physics, and in particular interpretations of quantum mechanics, that take that possibility seriously. That's the next talk.
Yeah, I want to mention one thing and then ask a question. The guy who wrote the Wolfram program showed to a bunch of engineers. He has this chart up here with the squares, and he has I think 8 squares, and he has says there's I think 256 ways that you can put them differently, and you put them, and like I'm going to guess the number, but it's wrong. Like number 178, he puts that in there, and he lets it run. And then the most amazing thing happens, which shows to me that the universe is both orderly and chaotic. It's a cosmos and a chaos. Down the middle comes a white line. On one side comes repeating geometric shapes. On the other side comes total randomness. You get complete order and total randomness out of the same command.
Yep.
Now, my question is, I've read about this AlphaZero in this Harari book that we wrote. According to Harari, this AlphaZero can defeat any other, and he goes through the list of computers that it defeated, and he says that this AlphaZero is nothing but a set of algorithms, and that you feed into it the rules of a game, such as chess, and it can beat any other game or any other, computer or anything that plays chess. And you've never taught it actually how to play chess. He says it teaches itself how to play chess in 4 hours by playing against itself, and then it can beat any other computer. So this says, if it's true, and that's what he claims, and apparently Google is doing this. So can you think of how that meshes with this business about elegance and computability? Because apparently it's just a set of algorithms, and I don't know that they worried about it.
Let me talk about the Wolfram thing first. So what Wolfram did is basically invent another way of building a Turing machine using cellular automata. And it turns out that one of these machines does some very interesting stuff. I think he's overblown the significance of it, but it does point to an interesting way of interpreting all these negative results, that you can't prove that mathematics is consistent and complete, and you can't solve the halting problem. All these things that you cannot do. One way of interpreting that is in a positive light, which is that mathematics and computation, they're very closely related. They're both, in some sense, infinitely rich. If we could come up with this mechanical way of doing math, we'd just be done. We'd just build a computer mathematician, and we would just feed it theorems, and it would spit out proofs. But we know we can't do that, and so there will always be new discoveries to be made in mathematics and computing, no matter how long we are at it. And we can prove this. And the fact that we can prove that there will always be new discoveries to be made, I think is really fascinating and kind of inspiring, personally. Let's see, what was the other, oh, the chess playing thing. Yeah, I think that would probably take us too far afield. Let's deal with that offline.
So I've actually heard the proof that you can solve the halting problem. And it has to do with, I'll try to describe it very quickly, but when you have a Turing machine, it has basically a set of states. And if you had another Turing machine that could just basically track the states, if it ever ends up in the same state, you have to be in a loop. The problem is you could just write a random number to the tape, right, and you would always be in a new state, which is how it works. And of course, the Turing machine, by definition, has an infinitely long tape. So there it doesn't work, right?
Yep.
Well, in reality, you can't make a Turing machine with an infinitely long tape. So eventually what would happen is you'd run out of tape and the program would halt because it would throw an exception.
Yep.
So the solution is you can actually do it because you can always make a bigger machine that can track all of the states of the smaller machine
one of the
in
ways
principle.
One of the ways that you could solve the halting problem is if you could build a Turing machine that was infinitely fast. So you could imagine a machine that did its first step in 1 second, and the second step in half a second, and its third step in a quarter of a second, and keep getting faster and faster and faster, so that by the time you get to 2 seconds, it will have done an infinite number of computations. And so if it's still running after 3 seconds, you know that it's not going to halt, right?
Right, yeah.
That kind of imaginary machine has a technical name for it. It's called an oracle for the halting problem. And you can imagine such things, and mathematicians do. And there's a whole branch of mathematics that thinks that studies what would happen if you had an oracle for the halting problem. And all kinds of interesting things happen. I could do a whole talk just on that. Like I said, mathematics is infinitely rich.
In relation to your mathematics is infinitely rich stuff, one of the other consequences of Gödel's theorem is that that if the system is consistent and supports arithmetic, then it has certain statements in it that have no proofs. And so mathematicians are constantly fascinated by things up until they prove Fermat's theorem. For instance, there was a lot of speculation and conjecture that this was, because there's no way of knowing which statements those are going to be.
Not just statements that have no proofs, because that's not very interesting, because false statements have no proofs, right?
Well no,
the interesting thing is
statements that are true and there's no proof, right?
Have no proof.
There are theorems that have no proofs, and
well, they're not theorems because by definition, a theorem is something that has a proof. It's statements that are true, that humans can see are in fact true,
okay,
but
fine.
what you cannot prove. That's
but
the interesting.
The fascination is that the theorem precludes the fact that we would know which statements those were.
Well, that depends. So this gets into another philosophical question, which is, are humans Turing machines? Or do we have some kind of magical quality that allows us to transcend a Turing machine? So maybe the human brain is an oracle for the halting problem. Science cannot definitively rule out that possibility just yet. I personally give you long odds against. But
which gives you back the machines that compute over. Which gives you back machines that compute over things other than the integers.
Yeah, right. Yeah, exactly.
Okay, so we're going to make this the last question because we're just up almost against 12:15.
Can you talk about the Turing test? I think it's a test of are you doing something with a computer or is it a person?
Yeah, the Turing test has nothing to do with any of this. It's a test for deciding whether or not a machine can think or is sentient. And the test is basically you have a chat with it, not face-to-face, but using email or something like that. And if the computer can convince you via email that it's a human, then it's sentient. And of course, you can't prove that. That was just a criterion that Turing suggested as a way that we could use for deciding whether or not a computer is intelligent or can think or is sentient. But whether or not you accept that or not is, that's a philosophical question.